Hello everyone. In this video we will be giving an introduction to infinite series. So a series, or infinite series, we'll usually just say series, is an infinite sum, right? So for example, you could have 1 plus 2 plus 3 and so on, which we could write more compactly in sigma notation as n equals 1 to infinity of n. And in general, for most series, all series, we can write them like this. N equals, maybe we want a starting point other than 1, and so I'll just put a k here, to infinity of some an, where our an is a sequence. Okay, so let's look at a couple other examples then. So for instance, we could have n equals 1 to infinity of negative 1 to the n. One that will be especially important is this one, just as it was with improper integrals, with 1 over x from 1 to infinity, 1 over n. This is what's called the harmonic series. This will play a crucial role for us. And one other example that we're going to look at will be this series here. So these are all just examples of infinite series. You could write out some of the terms, but usually we prefer sigma notation just to be compact. So now we want to look at what it means for a series to converge or diverge. So this is going to be somewhat similar to improper integrals, right? So with improper integrals, right, if we looked at the integral from 1 to infinity of f of x dx, like how did we do this? Well, we took the limit of these definite integrals, right, which we had no problem computing, and then we would just take the limit as our upper bound of integration went to infinity, right? So took the limit of these things that we could compute in order to compute this infinite thing. So we're going to do something similar here, where we again want to take these finite pieces, these computable pieces, and then take a limit. So right, if you're thinking of this picture, maybe we have something that looks like this, and we care about all this area over here. Well, what is the improper integral saying? It says like, okay, take it from here to here, and then take it from here to here, and then take it from here to here, and so on, right? And you just keep going out, and you take all of these finite pieces. Okay, so if I write out a sum, I've got 1 plus 2 plus 3 plus 4 on forever. Well, what do my finite pieces look like? Well, it looks like, hey, I can stop at 4. Hey, I can stop at, 5 over here, or I can stop at 6. And you can keep going, right? And each of these is individually computable, right? 1 plus 2 plus 3 plus 4, that's pretty easy. That's 10. Add a 5 in there, get 15. Add a 6 in there, I get 21. And you can kind of just see, okay, what is happening to these finite sums as I take more and more summands, right? And so this leads us to the definition of what is called a partial sum. Okay, so go ahead and let this be the series that we're talking about. Then the partial sum Sn is equal to a1 plus a2 all the way down to a sub capital N. Basically, you're just taking the sum of the first capital N terms here. Okay, so another way to think of this is, if you want to keep it in sigma notation, you're just going n equals 1 to capital N here. Okay? Of these ANs. So why is this useful? Well, what we said is basically, if you take the limit as having more and more terms that you're adding up, that should be where your infinite series goes, right? So then we actually define our series to be the limit of this sequence, right? So this is a sequence itself, depending on capital N. So we say that our series of the ANs is equal to the limit as capital N goes to infinity of Sn. And so now we can use all the techniques we had for sequences to determine whether or not our series is going to converge or diverge, right? And so we say that the series converges if this limit exists and diverges otherwise. Okay, and so now let's go back and look at those examples that we had and see whether we can figure out a formula for these partial sums and then determine whether these series converge or diverge. So first, let's look at the series, the sum from n equals 1 to infinity of n, right? So again, this is just like 1 plus 2 plus 3 plus 4 and so on forever, right? So what do our partial sums look like? So when I'm looking for these, I'm usually just going to write out a few, right? So S1 just means, well, my first one term, that's 1. S2 is 1 plus 2, so this is 3. S3 is 1 plus 2 plus 3, which is 6. And you may not see the pattern here, but this one I'll give to you. So this is actually just the sum of the first capital N positive integers, right? And it turns out there is a nice formula for this, and it's exactly capital N times capital N plus 1 all over 2. And you can check that with the first few terms there if you want. There are a couple of different ways you could prove this, but we're not going to do it here. But we do want to look at the limit, right? So let's take capital N to infinity of our partial sum. So n times n plus 1 over 2. So what's going to happen? Well, I mean, our denominator is just staying 2, and our numerator grows without bound, right? And so this is going to be infinity. And so this series diverges, right? Our sum just keeps getting bigger and bigger and bigger. We're adding bigger and bigger numbers, and so we're not going to approach some finite limit. Okay, so let's look at one that's maybe a bit stranger. So let's look at this series where we're switching signs every time. Okay, so we're going to go, well, what is this first of all? Let's write out some terms and see what's going on. So it's negative 1 to the n. And in this case, we're starting with a negative 1, right? Because we start with 1 as our power, so an odd power. But then we get an even power. So we're going to get plus 1, minus 1, plus 1, minus 1, plus 1, and so on, right? It's going to keep switching between minus 1 and plus 1. So what are our s's here? What are our partial sums? So we're going to end up with a formula here in a second, but let's see. S1 is negative 1, S2 is 0, S3 is negative 1 again, S4 brings it back to 0. And this is going to keep happening, right? You're going to have negative 1, then you're going to add 1 to get to 0, you subtract 1 again, you add it back to get to 0. And so we can see this is piecewise defined, right? So basically for all of my odd n, I'm going to get a negative 1, and for all my even n, I'm going to get 0. So if I want to consider the limit of this sequence as I go off to infinity, well, I'm just bouncing between negative 1 and 0, right? So if I'm like graphing this sequence, all I'm doing is going boom, 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 and so on, right? And since I'm not approaching either one of those values, but instead bouncing between them, this just doesn't exist. And so we would again say that this series diverges, but it's definitely a different kind of divergence, just as we saw with some of the improper integrals, right? So this one, in number 1, goes off to infinity. It grows without bound, whereas this sum does not grow without bound, right? It's actually just always either negative 1 or 0. It just doesn't happen to converge to a single value. All right, so we're going to look at one last example here, and this is called a telescoping series. So why? Well, let's find out. So suppose you had to do an integral instead of a sum here, and you saw like an x times x plus 2 in the bottom. Then one way you might think of doing that is by partial fractions. And it turns out that is indeed the way to think of this. So how can we rewrite 3 over n times n plus 2? Okay, so I went ahead and did the calculations already, and so we get a is 3/2 and b is negative 3/2. And so we can rewrite this sum then by splitting up the terms. Okay, so this is the sum from n equals 1 to infinity of 3 over 2n minus 3 over 2 times n plus 2. All right, so now let's start looking at some of these terms, right? So let's just start writing some things out. So S1, well, I'm just going to add up my first term, right? So I have 3/2 minus 3/6, or 1/2. Okay. S2, I'm going to have that same term, right, from n equals 1, plus my n equals 2 term, which is 3/4 minus 3/8. S3, I'm going to have, again, these two terms. But then I'm going to add in n equals 3, so 3/6 minus 3/10. But now, did we notice something here? So we have a plus 3/6 and a minus 3/6. Something to note. Let's do one more. So here we have one more term, and now notice we have the minus 3/6 plus 3/6, so these guys go away. Plus 3/8 and minus 3/8, these guys go away. And this is going to keep happening, right? So in S5, we're going to cancel out the 3/10. In S6, we're going to cancel out the 3/12. And this keeps going and going and going, right? And so what do we see happening in general? So for Sn, I always have my 3/2. And if n is greater than or equal to 2, which since we're taking it to infinity, we might as well consider those, we also will have the 3/4. And those two never get canceled, right? Those two never get canceled. But everything else will eventually, right? The 3/6 does in S3, the 3/8 does in S4, 3/10 in S5, 3/12 in S6. And in general, we will cancel everything but the last two terms, right? So here it was 3/8 and 3/10 remained. Here it was 3/10 and 3/12 remained. And what are those in general? So we have 3 over 2 times n plus 1, right? Because we're basically plugging in capital N minus 1 to n plus 2. And so the plus 2 and the minus 1 give you a plus 1 there. And then when capital N is plugged in, we get 2 times capital N plus 2. Okay? So then what is the limit as n approaches infinity of this? Well, the two terms on the right here, right, the ones circled in green now, both go to 0 because the denominator goes to infinity. And so we're just left with 3/2 plus 3/4, which, if you want to get a common denominator, right, this is 6/4 and 3/4, and so we get 9/4. And so in this case, we have a series that converges, and it converges exactly to the value 9/4. And hopefully you can see why we call this telescoping, right? It's that as you look farther and farther out, you're going to see these cancellations going on. And so it's this farther and farther out part that kind of gives it the telescoping name. You see a lot of repeats in the pattern. Okay, so here are your two exercises. So just going to have you look at two different series and find the general formula for the partial sum. So S capital N. And then for both, answer the question, does the series converge or diverge? And if it converges, to what value does it converge? Okay, and for the second one, again, you may want to look at that form and think, is there a way I can rewrite this that might be helpful? Thank you for watching.